We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
The Space Shuttle Discovery, part rocket, part spacecraft. And after falling through the searing flames of re-entry, it becomes a computer-controlled glider. On takeoff, the shuttle is hurled into orbit by engines that have the power of 44 jumbo jets at full throttle. Yet it returns to Earth on nothing more than a cushion of air.
Discovery on energy at the 180.
Copy, on at 180.
Welcome home.
And Discovery's glad to be home.
Within hours, NASA engineers and technicians will begin preparing Discovery for her next flight. Boarding the shuttle when she's once again hauled to the launch pad will be a Canadian astronaut who's been standing in line for 15 years. At the Johnson Space Center in Houston, Canadian Bjarni Tryggvason prepares for his rendezvous with Discovery. He was one of the 6 original Canadian astronauts selected in 1983. Now, finally, he has his mission. Payload specialist on flight STS-85. An opportunity to join the world's most exclusive club.
When you're training for these missions, you're going to do something that is, very unique. You're going to sit on this incredibly big bomb that's got 5 million pounds of explosives in it. And that's going to be lit and released in such a nice way that it just takes you zing up into space.
Bjarni and other aspiring astronauts are not deterred by the fate of the Shuttle Challenger, which broke up in mid-flight in January 1986. All 7 crew members perished.
Obviously a major malfunction.
Challenger's fiery end was a shocking reminder of the dangers of space travel, the hazards of riding on the back of a giant bomb. So Bjarni lives with the memory of Challenger. He calculated the odds long ago.
The Challenger was, an unfortunate accident, and there were some engineering plus management things that brought that about. You know there are risks, and your job and the job of all the other people is to minimize those risks. You really have to assess your reaction to those risks before you get into the program, not afterwards. And you can't change that assessment based on one accident.
NASA was overconfident with the Space Shuttle program. The shuttle was the first spacecraft designed without a crew escape system. After Challenger, NASA introduced a primitive system, disturbingly similar to the escape hatches used by World War II bomber pilots. Astronauts again wear pressure suits and parachutes on takeoff and landing.
If you're on the ground, if something goes wrong, you need to get out of the orbiter, you have to be able to do it while carrying and wearing this 90-pound launch and entry suit. So we go through a number of scenarios where you do emergency egress out of the side hatch of the orbiter.
80% of astronaut training today is devoted to safety. Bjarni Tryggvason is a typical astronaut, an engineer, mathematician, fluid dynamics specialist, university professor, and a pilot. He sees his space mission as an opportunity to combine his 2 passions, science and flight.
being able to do the two together by flying the science you're working on in space, I think it's just fabulous. You know, you couldn't hope for a better mix of doing things that you love to do.
Bjarni, at 51, will be making his one and only space flight. For the orbiter Discovery, it will be Flight 26. The space race began in 1957 when the Russians launched Sputnik. Bjarni Tryggvason's boyhood imagination was fired by the small metal satellite with its beeping radio signals.
I guess the first time it occurred to me that this may be something that you could do is actually when Sputnik was launched back in 1957. I was 12 years old then. And I remember standing on a hillside in Kitimat, BC, where we lived, and you could see Sputnik going over the horizon, over the mountaintops. And it was just amazing. It was to have the world was kind of an ordinary place one day, and all of a sudden there was something up in space, which is something that most people had just never even dared think was possible, and all of a sudden it was there.
When Bjarni was growing up, Canada didn't have an astronaut program. He sustained his dreams of space travel by becoming a pilot.
Right after high school, the first thing that I spent my money on was learning to fly. And I was just going straight for a commercial license. I wasn't just learning to fly. I was going to go fly and fly airliners and work as a pilot all my life.
Bjarni has logged 4,000 hours. He's an accomplished aerobatic pilot, and he enjoys cross-country flying in a twin-engine Beech Baron.
It's a challenging thing to do. It's difficult to do it with precision all the time because the flying demands all of your attention, and it allows you just to put aside everything else that you might have cluttering up your mind at that time. I find it, in fact, not only challenging but also relaxing.
NASA uses T-38 jets to assess and train its astronauts because flying demands discipline, self-control and quick responses. Bjarni teams up with Kurt Brown, who will command the Discovery for this mission.
Almost guarantee you won't. 090 at 2,000 feet, we'll just go back around for another one.
It gives him a chance to see how well I conduct myself and work through flying in the T-38.
Kurt Brown is a veteran astronaut. The Discovery flight will be his 4th shuttle mission.
The only really basic training to do on a continuing long-term basis to keep yourself prepared for flight in space is flight training. NASA uses the T-38 jets to keep all of their people current on instrument flying in a reasonably demanding environment where you need to be wearing oxygen mask and helmet and parachute. That kind of get you prepared to work naturally with that kind of equipment on, just the way you have to be able to work easily in the launch and entry suit on the shuttle. The instrument flying really teaches you how to communicate and work effectively with you as a crew member in an aircraft, or later on in the spacecraft, with the support team on the ground, which in the aircraft is the air traffic control system, and when you're in the spaceship, it's the mission control team is on the ground.
Like many scientists, Bjarni was intrigued by the plans for an international space station. His research led him to the discovery that most scientists had miscalculated the nature of the space environment.
They assumed that it was a perfectly clean environment. You put your experiment into space and it would be a perfectly zero-G, stress-free environment. Well, when you build a big structure like the space station, it has a lot of dynamics where it'll kind of shake like a bowl of jelly, if you like, because of all the things that are going on there.
Bjarni decided to create the ideal environment scientists had anticipated. He is the co-inventor of the Motion Vibration Isolation Mount, or MIM. With the use of magnets, MIM creates a floating platform for experiments. One of Bjarni's MIMs was delivered to the Russian space station Mir, where it operated trouble-free for a year. Bjarni has taken a new model MIM to NASA's Lewis Research Center in Cleveland. This will be the final test of the equipment before it's launched on Discovery. It's loaded aboard a DC-9, used to simulate the microgravity environment of space. For Bjarni, this flight is critical, a last opportunity to tune the equipment before he boards the space shuttle. NASA's DC-9 has a standard airframe, but its engines have additional thrust. The aircraft creates a weightless environment by flying in a series of parabolas or arcs.
Well, you only get 20 seconds of weightlessness in these airplanes in little shots. You do 50 parabolas in a flight. You can learn a lot of things about how the experiment is going to look. You can learn a lot of things about how easy it is to carry out some of the procedures that you're going to do in weightlessness.
First time in space.
The scientists aboard the DC-9 will be Bjarni Tryggvason's ground support team when he's in orbit.
I let all the other researchers and the people that are helping us carry out all the operations, and I just kept an eye on looking for what's happening. Spent a bit of time with each of the 5 or 6 experiments we're doing, floating around doing that. I can see what kind of motions am I expecting. Any things that look like they're going to be awkward to operate in space. So it really drives you to doing everything you can to perfect your technology.
Oh, Bjarni! Yeah, you thought something. We have a secret.
With the final test of the MIM, Bjarni's 15-year wait is almost at an end.
It would have been much nicer had it come a lot sooner, but I've never lost faith in the fact that these experiments would fly and that I would get a chance to fly with them.
But the shuttle that Bjarni will ride into space has a checkered history.
Welcome to space, ladies and gentlemen.
Welcome to space, aboard the astonishing, reusable American Space Shuttle. Development of the shuttles was long delayed by a headlong space competition with the Soviet Union. Instead of shuttles and a space station, the Americans raced to put men on the barren surface of the moon to gain prestige in a bizarre Cold War contest sparked off by Sputnik. Multi-million-dollar Titan and Saturn rockets were used to catapult Gemini and Apollo capsules into space and were completely non-recyclable. A network of warships recovered the astronauts. They picked up the capsules as well, but only so they could be sent to museums and put on display. Having won the space-age publicity battle, the United States pursued a more rational approach to space exploration and planned for a permanent orbiting space station. Maxime Faget was NASA's Director of Engineering and Development.
When we got to looking at the transportation to the space station and back, we thought, gee, that's going to be a great number of flights going up that space station. It's going to be very expensive if we throw all the hardware away every time we fly. And pretty soon it became quite clear that to make a reusable vehicle was probably a bigger undertaking than the space station.
Faced with budget cutbacks, NASA postponed the space station. Engineers were told to build an even larger and heavier shuttle, capable of more tasks.
The requirements kept growing. We started off thinking maybe to go to the space station back we might need 10 or 15,000 pounds of cargo. Well, towards the end, we were designing for 60,000 pounds of cargo.
There were furious debates over the shuttle design. Faget wanted a straighter wing for greater control at subsonic landing speeds. His basic concept for the shuttle survived, but he lost the debate over the wings and still has reservations about their stubby delta design.
If I'd have had my way, as one of the people that was trying to influence the design, we would have ended up with less lift to drag ratio and with a wing that was better suited for landing.
The shuttle has to glide for 8,000 kilometers after entering the Earth's atmosphere. Getting it back to base in California at the right altitude and the right speed for a safe landing requires one of the most complex software programs ever written.
We were able to put in this autopilot that would make the shuttle fly like a good pilot would like to see an airplane fly. In other words, it had reasonably good flying qualities, and the flying qualities were not in the aerodynamics, they were really in the computer.
To be more cost efficient, it soon became apparent that the shuttle needed to be able to carry civilian as well as military satellites. Engines were required that could carry over 100,000 kilograms of shuttle and payload into orbit. The shuttle itself was given 3 liquid oxygen and hydrogen engines, the biggest reusable engines ever built. Many early prototypes blew up on the test stand. The shuttle requires solid fuel booster rockets. To save money, they had to be reusable. Built in Utah and 49 meters long, they're made in 4 sections so they can be shipped to Kennedy Space Center in Florida.
Each segment was built and put on a railroad car, and then the segments were put together once they got to the Cape. That's the one bad accident we had, is when the vehicles failed at one of these segments, the joint segment between 2 segments. I don't know whether we made a good decision in making that in segments.
Providing the shuttle with a heat shield to enable it to withstand the 1600 degrees Celsius temperature of re-entry generated another furious controversy. Max Faget encountered stiff opposition when he selected a shield of insulating tiles made from common sand. They were as light as balsa wood, and a hole could be poked into them with a finger.
So all the old timers that have been, some people have spent damn near a career working out good arrangements for metal shingles, and we were not using their solution. A few of us, I know that I was kind of leading the fight there for quite a while, decided that to go ahead and use the tiles.
The first shuttle off the line was the Enterprise. To the disappointment of Star Trek fans, Enterprise never went into space. It was hauled on the back of a 747 to an altitude of 9,000 meters and then released to glide to a landing at Edwards Air Base. 5 rehearsal flights was the total extent of in-flight testing. 2 astronauts were assigned to take the second ship, Columbia, into space and back.
When they finally got ready to make the first flight, it was a real nail-biting situation. We worrying about whether the tiles would fail. We had a lot of guys predicting the tiles would all fall off during the flight, and then of course we were worried about whether the flight control system would work fine. So it was a very dicey situation. I can't help but think that when John Young and Crippen went up, that they were sure depending a lot on that no pilot in modern history has to take so much for granted as those 2 guys did when we flew. They really had the right stuff.
John Young was named commander of the first shuttle mission. Young had the right stuff. He'd spent more than 500 hours in space and was a veteran of the Apollo moon landing program. In fact, Young was on the surface of the moon when he first heard about the plan to build a space shuttle.
They announced it while I was on the moon that they were going to apply the space shuttle, so I thought that was a neat idea, and when I came back and after I finished working on Apollo 17, I got to support the space shuttle from 1972 on, so I was very familiar with the design of it, and it looked pretty solid. You know, I knew it was a big step, and everybody was going to take a big step, and we were all willing to do it. And shoot, there was 20 astronauts in the astronaut corps that would have killed to be on that first flight. I'll tell you, they were all ready to go.
In April 1981, John Young and Bob Crippen entered the shuttle Columbia and were launched on a 2-day mission. The mission had been delayed 18 months after some of the tiles fell off. There were computer malfunctions, and 2 men died when they entered a nitrogen-filled shuttle compartment. There were many unknowns. NASA were not even certain where to jettison the booster rockets.
When you go straight up, you have to thread a very thin needle, because if you get too far off one way or another, you can tear the wings right off. And so you have to be very careful. And we have to measure the winds. We have to compute the loads on every mission to figure out what will happen. And on our vehicle, when we launched, we went and staged 10,000 feet high, and that's because we didn't really understand the aerodynamics of the thrust loads that gave us, and we learned a lot on that flight.
In the end, all went well. Young and Crippen settled into orbit 208 kilometers above the surface of the Earth.
Columbia, Houston, you guys did so good, we're going to let you stay up there for a couple of days. Your GoPro on orbit.
One of the first tasks for the astronauts was opening the payload bay doors. Young and Crippen opened the doors and turned on a camera. The images relayed back to Houston showed tiles torn off or damaged by the powerful vibration of the launch.
Well, as soon as we opened the payload bay doors, we looked back there and we saw about, let's see, I think it was off the left orbital maneuvering system pod, we saw about 4 tiles missing up there. And there was some off the right side, but not as much as on the left. And of course, when I looked at them, I said, oh my goodness, I wonder how many are missing off the bottom. Because that's where you worry about it. That's where your heat loads are. We didn't know what the heat loads were going to be when we got back. We found out later that they'd overestimated how much heat we're going to take. They predicted we'd get about 2,600 degrees on the nose, and we actually got 2,450 degrees. So when you make an error with your thermodynamics, that's the kind of error to make when you're in our line of work.
In the blazing heat of re-entry, the shuttle's radios do not function. Columbia, with 16 tiles missing and 148 damaged, emerged from re-entry blackout, safe and sound, heading for a textbook landing.
The space shuttle is a big glider. You come over the field, you have no engine, you're maintaining your energy, you go down, dive down, pull out and land.
More than 500,000 Americans converged on Edwards Air Base as word spread of the shuttle's tile problems. Millions more in the US and around the world watched on television. John Young aimed the 100,000 kilogram glider at the runway.
You're coming down at 20 degrees, which is 6 times steeper than an airliner. You're doing about 300 knots. You don't have much margin for error because you're going to hit the ground one way or another. From start to finish on the first mission, the vehicle worked just beautifully. We had practiced and practiced for all kinds of failures. And some of those malfunction procedures are 125 steps with multiple steps on each line, you know, so they're tough.
The successful flight of Columbia, the world's first reusable space vehicle, ensured a continuation of the shuttle program and gave NASA a new lease of life.
I thought that was a great thing to see that thing after it'd been up in space and there on the ground and looked almost just as good as brand new, which we'd never done before. You see, we landed it and we could fuel it up and go again. It's a pretty neat thing. So that was a very great moment.
The shuttle is the most complex flying machine ever built. In common usage, this winged spacecraft or orbiter is called a space shuttle. To NASA, a shuttle is the entire cluster stacked on the pad for launching. On the outside of the cluster, the orbiter and 2 solid-fueled booster rockets. At the center, a great orange-colored fuel tank.
It's an incredibly large craft for getting into space. So much thrust required that you have to get this 7 million pounds of thrust out of basically 5 engines. And that's, compared to, say, an aircraft engine on the 747, one engine on the shuttle has 10 times the thrust of one engine on the 747. So it's an incredible amount of power that the system is producing to get up there. So it's really kind of hard to believe sometimes that it's real.
The recoverable boosters, burning fuel at the rate of 10,000 kilograms every second, provide most of the thrust, then drop away to parachute to the ocean. In 8.5 minutes, the shuttle is in orbit. Astronauts go to work as soon as the shuttle is placed in a sustainable orbit. Joe Engel is a veteran astronaut and commander of 2 shuttle missions.
One of the first things we do is to open the payload bay doors, partly to expose the radiators, which are inside the payload bay doors, and they reject heat from all the avionics and all the parts that, and our own heat that we generate as a crew inside.
Once in orbit, the shuttle's internal engines are shut down. Gravity holds it in orbit as it circles the Earth every 90 minutes.
In orbit, we have to be going about 17,400 miles an hour. That is kind of a fixed velocity for anything that's in orbit at that altitude, 250 to 300 miles above the Earth. The speed that you have to go to stay in orbit is just equal to the pull of gravity.
Normally, the shuttle orbits upside down, its insulated belly facing outer space, to reduce stresses caused by 230 degrees Celsius temperature differences between sunlight and shadow. But if required, it can fly in any position.
Doesn't make any difference what attitude we're in as far as nose being forward or being right side up or upside down. There's no atmosphere. So the space shuttle feels just as comfortable going nose forward or sideways or tail forward or upside down or flat into the velocity vector. And the attitude that we fly really depends on what experiments we're wanting to perform. Sometimes we even rotate it in a barbecue mode so that it heats up evenly all over.
When it's time to return to Earth, the shuttle's orbital maneuvering engines are fired for 2.5 minutes to slow it down. This maneuvering burn is controlled by computer. The trajectory heading into the atmosphere must be accurate to within a few tenths of a degree. If the re-entry angle is too shallow, the shuttle will skip like a stone on water. Too steep, it will be torn apart by high G-forces.
So we turn the vehicle backwards and we fire these little deorbit engines or orbital maneuvering engines. They're 6,000 pounds thrust. And we slow up about 330 feet a second.
That's about 320 kilometers an hour, but it's enough. And at the lowest point of its oval-shaped orbit, the shuttle encounters the atmosphere. Astronauts are then treated to a light show, superheated air streaming around the fuselage and wings. Then it begins its 8,000-kilometer glide.
You intersect the atmosphere someplace over Hawaii. It's about 5,000 or 6,000 miles away from you going to land, and then you start gliding in and slowing down the whole way. The shuttle actually does some very slow but big S-turns just to chew up the energy that it has to get rid of in order to be able to land. There's no way that you could have a person, say, flying the shuttle through that whole thing, because you're 5,000 miles away from the landing spot, so you couldn't judge how you're doing. So the computers have to do all of that. You're 4,000 miles away and doing Mach 12. 30 seconds later, you're 3,000 miles away. You've covered 1,000 miles in a matter of a minute or so. You're still doing Mach 2 when you're 30, 40 miles away from the landing site, and you're up at 70,000 feet and coming out of the sky like a rock.
Well, we come over the field about 45,000 feet, just about subsonic, depending on how much turn angle we have to do. We line up with the runway then by the time we come through about 10 to 12,000 feet.
The mission commander takes the controls 1 minute from touchdown, when the shuttle rolls out of its turn to final approach, and he can see the runway.
We start the pre-flare, start to pull the nose up to arrest the sink rate, and very gradually shallow out and come in low, put the gear down at about 400 feet above the ground, because we don't want that down any earlier than necessary. That creates more drag, and drag is not what we need at that time.
The runway used by the shuttle is 5 kilometers long, and one pilot, coming in high and fast, didn't stop until he reached the end of it.
Once we have the main gear touched down, we put the drag chute out, start to lower the nose down, and once we get in the 3-point attitude, then it's just steering the airplane down and braking it down the runway, just like a conventional airplane.
"10 minutes after touchdown, a NASA recovery team 150 strong takes control, swarming over the shuttle looking for damage, the beginning of a long maintenance process before the shuttle's next flight. NASA's project manager of orbiter engineering, Calvin Schomburg.
A crew immediately goes out and walks the vehicle down, inspects it, to see whether or not there's been any major damage for all of the systems.
A day or two after landing, the shuttle is towed into an enormous 3-bay workshop called the Orbiter Processing Facility, or OPF. Here, every system will be tested and retested before the shuttle is ready to fly again. The average turnaround time is 90 days. On re-entry, the shuttle encounters temperatures that can turn metal into liquid. All that protects it is a thermal blanket and Max Faget's tiles. They come in 22,000 different sizes, each tile precision molded to find the contours of the shuttle. 500 people are dedicated to work on the tiles.
Every tile is different. Every tile has its own part number. Each tile has its own exact size. So when they put them on, they have to go make that tile.
The tiles must be protected from rain. Water makes them more vulnerable to damage and destroys their effectiveness in dissipating heat. In the early days of the shuttle program, NASA used Scotchgard to protect them. Today, they're injected with a waterproofing material.
We inject with a needle, just like a hypodermic syringe, except they have an automatic tool that injects 2 cc's into the tile. A normal tile weighs about 1/2 pound. If it rains on that tile with no waterproofing material in it, it'll weigh about 7 pounds.
The orbiter, its rocket boosters and the fuel tank are brought together in one of the world's largest buildings. From floor to ceiling, it's 160 meters. Clouds have formed and rain has fallen inside the building. A 254,000 kilogram bridge crane hoists the orbiter vertically. The fuel tank and booster rockets are already in place, and in an operation that takes 12 hours, the orbiter is slowly dropped into place and coupled to the fuel tank. The rockets undergo a 2-year refurbishment after being fished from the ocean. Only the fuel tank is new. The tank burns up when it falls to Earth. The shuttle stack is put together on top of the 2-story mobile launcher platform. It's hauled out to the launch site by a crawler transporter built to move the gigantic Saturn V rockets that sent the Apollo missions off to the moon. The transporter weighs 2,700,000 kilograms. Its 4 double-tracked crawlers are 3 meters high, and it burns 10 liters of diesel fuel every second. At 1.5 kilometers an hour, it makes its way down the 5-kilometer crawlerway to the launch site.
People think of it as an old spacecraft because it's 20 years old now. But the whole way the system works was just a totally computer-operated machine. And a lot of the times that the commander and pilot are operating, they're really giving commands to the computers, and the computers do all of the actual control of the shuttle. There's no craft, there's no airplane or no other craft that is as complex as the shuttle is.
On the eve of flight STS-85, the shuttle Discovery is ready for launch. With Discovery in the background, a time for goodbyes at Kennedy Space Center. Today's astronauts no longer have to adhere to the squeaky clean image of the space race days. Bjarni Tryggvason is divorced. His children, Lauren and Michael, wave, but can't approach him because of quarantine.
In a sense, it's a little disappointing that you can't be with him prior to the launch. It's nice to know that the people are there. And I'd seen a number of shuttle launches, so I kind of knew the kind of emotions they would go through. And I knew that a lot of them didn't, because they'd only seen it on TV, and it's really a totally different experience to see this live when the shuttle is there. There's no instant replay or anything like that. And then when it goes off, it has this incredible, tremendous power.
Discovery Houston for the CDR and PLT comm check on air to ground 1.
PLT, last clear, air to ground 1.
2 weeks before the launch, we went through the complete scenario, including getting up early for breakfast and putting on our suits and going out to the launch pad and getting the shuttle and all that. And so now on the real day, it seemed really that you're doing another simulation.
The crew of Discovery gets a cheer on its way to board the shuttle. Commander Kurt Brown leads the way, followed by Bjarni, whose 15-year wait is almost over.
All continues to go well aboard the orbiter Discovery out at the launch pad and here in the firing room.
Go ahead. Can we get a QC on 143, please? Sure.
And the first time it really took a turn away from the simulation was about 5 minutes before the actual liftoff, when they start testing the elevons. These are the control surfaces on the shuttle. They start gimbling the engines, because each time they do that, they send a little shudder through the shuttle. And it's like this thing that you were always doing simulated activity and before. All of a sudden this big beast is just starting to come to life.
MPD, you are clear to launch. Copy that, sir. Thank you. Go for OAA retract.
You get into the sort of last 30 seconds and the countdown of 15 seconds starts. Pretty incredible time, and you're just hoping, finish it, let's go.
10, 9, 8. We have a go for main engine start.
The main engines come on 7 seconds before liftoff, and there's a tremendous sort of thump in the system, and it vibrates and shakes, and you feel it now moving, and then right at liftoff the big engines come on. And it's just like a big football player hit you in the back, only now he keeps pushing you, and there's no end to that push, and you're just being pushed into space. You have no sensation of speed, but you're sure you're being pushed someplace in a hurry. Within about 30 seconds, you hear on the radio you're through 50,000 feet in Mach 1.
34 seconds into Discovery's 8.5-minute climb to orbit this morning.
And it happens so fast. The speed build up and the altitude climb happens so fast that it's kind of hard to keep up to, even as you're in there listening to it and experience it all.
Discovery, go at throttle up.
Copy, go at throttle.
And telemetry currently indicating all 3 main engines, auxiliary power units, and fuel cells continuing to perform well. Discovery now at a speed of 2,800 miles per hour. Downrange from the Kennedy Space Center, 27 miles.
Pretty amazing that you're up there. It's just an incredible experience, and if anything, it makes me feel kind of a little bit humble, because you're fortunate enough to be up there, one of the few people that get a chance to go up there, and you're up there because of the work of thousands of people on the ground, and without their efforts you couldn't be there. But when you look out at the edge and you see the horizon of the Earth and you see the curvature of the Earth, then you're really honing in on you're in space.
Although planned initially as a transport for hauling astronauts and equipment back and forth to a space station, the shuttle has proven to be a very effective platform for scientific experiment.
It's an amazing vehicle. You can do an incredible amount of work with it, and the big advantage it has over, say, the Soyuz spacecraft or the Mir that the Russians have, is that you can take all your hardware up there, you can do your work, and then you can bring all your hardware back. And so then you can look at your results see what they're like, tweak your hardware a little bit, send it back up again. And the shuttle is the only spacecraft that allows you to do this.
Time in the shuttle is valuable. Every mission costs almost $500 million US. So Bjarni goes to work almost immediately, adjusting to the weightless environment as he starts his MIM and sets up scores of experiments.
In the spacecraft, you're just floating. And you can just, if you let go carefully enough, you can hang in the middle of the cabin like for several minutes and just don't move at all.
For a year, Russian and American astronauts ran experiments on the space station Mir using Bjarni's MIM platform. Now, after long months of frustration, he gets his turn.
I've been working the past year and a half training the cosmonauts to run MIM on Mir, and now I had a chance to actually do it myself, and it was really nice to see your own system working. And I could see, because we can actually display the performance on the computer screen right as we're operating. I could see right away that we're getting really good performance out of the systems.
Bjarni is a dedicated scientist. There are times aboard Discovery that he becomes so focused on the science that he forgets he's spinning through space.
I was keen on trying to complete as much as I could, so I really worked from morning till night, basically pretty well every day to try to get all this stuff done. I could have just as well been in the lab because I was just having to work so fast and so continuously that you get kind of lost in that. And then every now and then, you're floating. Just a little thought goes through your head, wow, you're in space as you're doing this. But we did a lot of runs and a lot of good ones, I think.
NASA always asks astronauts to take photographs when they have a few spare moments. Shots taken by humans have proven to be more interesting and of far greater promotional value than those taken by remote cameras.
One of the things I found really fascinating was to look out over the ocean, and there's this nice pretty blue, and you can see the edge of the Earth in the distance and a little bit of the atmosphere. But you see the clouds standing in this sort of a three-dimensional structure over the oceans. And it's just really an incredibly pretty sight.
The Middle East, with the Mediterranean offshore. The city of Montreal on its island in the St. Lawrence. And a rare photograph of the aurora in the southern hemisphere, the Southern Lights. For scientists, the shuttle's microgravity offers an exciting new environment for an enormous range of experiments.
Working in space gives a brand new kind of lab, and it adds its own unique little window which will allow us to better understand some of the things we do on the ground.
Bjarni is convinced that when the International Space Station goes into orbit, a version of MIM to dampen the vibration that might ruin experiments will be on board.
These kind of systems will be on a space station without any question at all. They may not look like the one that we flew, but they'll work on similar principles and they'll do the same kind of job.
For Bjarni, the entire experience was well worth the wait.
Yeah, I've been working towards this for not just 14 years, for about 30 years, I'd say. It's been a lot of effort, a lot of time, but I think the experience was just an amazing, unique experience. I could have been doing the research of the type that I'm doing at a university or at the National Research Council where I was working, but this gave me a chance to do that kind of work and fly in space. And I'd say the long years of working towards it, it was certainly worth it. Anybody who wants to do this, I'd say go for it because it's an amazing, amazing experience.
An amazing experience. Bjarni Tryggvason inspired as a boy by Sputnik and the dawn of the space age. A dream of being one of the chosen few. It was a long wait, but he finally realized his dream and in the process advanced the cause of science.